Okay, in this part, we want to look at what we call climate feedbacks. These are things that will either amplify or decrease changes in temperature. Um, one of these would be what we call the albedo, the reflective qualities of the Earth's surface, for example, is one of these. So these feedbacks then are these processes that either amplify or reduce climatic trends toward either warming or cooling. And again, mostly natural. So one of the biggest ones is what we call the ice albedo feedback. Remember from previous chapters that the albedo is the percentage of insolation that is reflected back. And remember that white reflects more than black. Black absorbs, white reflects. And where we find much of the Earth's white surface is in towards the poles, where the temperatures are very cold, the water freezes, and we get lots of ice. This is what we call a positive feedback. Um, don't confuse, it doesn't mean that it's positive in the sense that it makes things better. It's just a positive feedback in that it affects the temperature. So if we get more insulation, for example, then the ice would begin to melt, and that would change the surface cover of the ice to dark ocean. So it would stop reflecting and start absorbing more. And remember, water can store lots of heat energy. So if we are absorbing more heat energy, this is this cycle then where we start to move that heat energy around in the water. We get more evaporation. We put more warm moisture into the air, and so that continues to warm up the temperature. So any decrease in ice then has this effect of adding to the warming of the atmosphere. Now, water vapor feedback, again, water is a greenhouse gas. We tend not to think of it that way, but it is. If you get more evaporation, that's more moisture in the atmosphere, so you have a higher humidity, like we talked about in previous chapters. That creates more clouds, and so we get that also. Clouds can either trap in long wave radiation that's going back into space and keep what's underneath it warmer, or can, in some cases, block the insulation from coming in. So notice here these white and blue areas where we get these high concentrations of water vapor. And again, here's Mexico and the southern United States. So these are often thunderstorms, but the more water there is in the atmosphere, the more rain, and therefore oftentimes if it's very warm, you get more powerful storms, more hurricanes, and that's mostly on the east coast of the US. And one that's in the news a lot is what we call the carbon budget. And this is the exchange of carbon between systems. And that's the global carbon budget. And because this is one of the things we want to keep in equilibrium. And so as the carbon moves from its source to its sink, we want this to balance out. We want the input and the output to balance out so the Earth stays in equilibrium. But the human impact on this, especially clearing forests, which produces more carbon dioxide, changes photosynthesis. It's had a dramatic impact on this, and that's why one of the reasons that climate change activists are always talking about the destruction of the rainforest, for example, because trees absorb carbon. That's why it's so important. Same things with the ocean, absorb a lot of carbon as well. And you want photosynthesis because things can grow more quickly. So here's kind of how that works. So trees breathe in the air, the carbon goes down into the soil or into the plant biomass, and they breathe back oxygen. And when you remove the trees, that carbon isn't absorbed, so it stays in the atmosphere and will contribute to climate change. And so this is what we know as the Keeling curve, where the increase of the CO2 concentration. Notice it's consistently gone up since they started measuring it back around in the late 1950s. So it's gone from about 310 ppm parts per million up to around 400 parts per million. And so again, that's putting more carbon into the atmosphere, and that's numerous factors doing that. You know, both the destructions of the forests, the cutting down, removal of trees, but also you know, human-induced pollution as well from factories and so forth. So, how do we know that there is climate change today? Well, we know this because we've been taking measurements over the past century, and all kinds of measurements, and they have shown these four things. One, temperatures are rising, ice is melting, sea levels are rising, and we have more water vapor in the air. And this is indisputable. And again, when you go over to your weekly module, you'll see all kinds. I think there's 3 or 4 videos on climate science, which talks, you know, in more detail about the science behind the study of climate. Um, there's one related to growing coffee and how that's contributed to climate change, and also climate change geopolitics. And all these things are related just to these four things. But again, we've been taking these measurements now for a long period of time. And as we see in the slides, they have contributed to not natural change, but human induced change. So again, we have more water vapor in the atmosphere. We have higher air temperatures. We have melting of glacial ice. We have higher temperatures over land. We have reduced snow cover, so then, you know, reduced albedo, more absorption, less reflection. Higher air temperature over the ocean, meaning more evaporation, puts more moisture into the air. Decreasing sea ice, higher sea surface temperatures. So if the sea surface temperatures are going up, again, that means the water's warmer. And if that is true, then ice starts to melt, you get more runoff from melting glaciers and so forth, and that contributes to rising sea levels, which means more water in the oceans, which also means more absorption of heat. So this is just how over the past century. So these are the areas where the temperature has changed. Now, white is 0. So anything in red, the temperature has gone up in some cases 3 degrees Fahrenheit. Okay, so over here, mostly in Central Asia, up here in the northern part of Canada and the northern United States, in the rainforest and so forth, but almost everywhere, temperatures have gone up over the last century from 1900 up to 2012. In some cases, as high as 3 degrees Fahrenheit. So from 1880, blue is the annual mean, okay, and red is the 5-year mean. And notice again this steady increase of rising temperatures. So here's 0 here. And so by 2015, we've gone up about 1.8 degrees. And 2011, 2015, those were the 5 warmest years ever recorded. And if we extend that back out to 16, 17, 18, that's, you know, become even truer. Those years were warmer than these years. And again, this is pretty indisputable, and it's not cyclical because it's happening so fast. Cyclical, you know, like the wobbly axis, the tilt of the Earth's axis, the elliptical orbits, things like that. Those are many, many thousands of years. This is like taking place in like 120 years. So when one thing we can actually see is melting ice, because now we have satellites in the air. We can do satellite photography, and we can see how, especially in the Arctic ice has dramatically decreased. It's, you know, here it is, minimum ice extent on 2012, and this used to be the minimum summer extent in 2000. So notice that we've lost all this. And now, you know, we have a true Northwest Passage. Ships can sail from Europe over the North Pole and over to Asia if they, you know, choose to do that, as opposed to having to go all the way around down here. Now they can just quickly sail across here, and that would dramatically decrease transit time for goods. Same thing in the Arctic. So notice that the change the redder, the more we've lost. Over here in Greenland, same thing. The redder, the more melting we've seen. And again, as this melts, it flows into the ocean and increases sea levels, which warms up the seawater. And again, seawater, ocean water can contain vast amounts of heat energy, so we get more evaporation, more humidity in the air, and so that makes the air warmer, which again contributes to the melting of the ice. So you can see, how much the Antarctic has lost and how much Greenland has lost. And these are both trending down, so it's, there's not going to be any change in this anytime soon. And we can see this also in what we call permafrost thawing. Remember last chapter we talked about these polar climates, and where you had tundra where for almost the whole year the surface was frozen, except for maybe a couple months in the summer it might thaw down to maybe 2 or 3 inches down. But now, as the atmosphere gets warmer, the thawing becomes deeper, and these projections, all this in blue and gray here, will be thawed out by 2100. And that releases more methane, again, which is a greenhouse gas. All these other, contributing factors that will add to the production of greenhouse gases. Rising sea levels. Again, as the ice sheets melt, that adds more water to the ocean, and sea levels will rise up. That heats up and that expands the volume of the ocean as well. So that also is part of sea level rise. And the more water we have in the ocean, the more heat the ocean can contain, can store. And again, notice, by all these have studies have shown that sea levels have risen. So here's the base. But by 2100, a lot of people project in some cases by as much as 6 feet. Even the worst one is only is down here, little in a range from a foot up to 3 feet, basically. That's the best case. And the worst cases will be up to anywhere from 2.6 to 6.6 feet in sea level rise. But again, these are all measurable things. We know this is happening. And over in the study module, there's a video on the nation of Kiribati in the Pacific, South Pacific, which is probably most people think will be the first nation that will disappear because of climate change, because of the increased sea level rise. It's not that the island will get drowned, will get covered up by water. It's that the wave action increases and will basically just wash the island away. You can see, there are Pacific atolls where maybe the highest point might only be 3 feet above sea level. And you can see as the tide gets larger, as the high tides get larger, it will continue to wash away the islands. More increased water vapor means more energy in the atmosphere, increased hurricanes, more powerful hurricanes, and we'll see those over the next coming years. More precipitation in some places. And again, hurricane strength. Again, if you put more water into the atmosphere, that's more heat energy in the atmosphere, more potential hurricanes, and the hurricanes will be stronger. And you can see, again, this is the baseline. So precipitation has been above mean pretty much ever since 2000. And as we get more water in the oceans, more evaporation over the oceans, more water in the atmosphere that will cool down has become precipitation. So we're going to have more heat waves, we're going to have more droughts, we're going to have increased precipitation, more floods. All these things are the direct result of present climate change. Not cyclical, but present climate change. Again, here's the drought severity. So areas in red, the droughts are going to become more severe. Notice here in California, we're kind of okay for now, but the main concern is over here in Africa, where the droughts have become so severe that we're actually getting the first migrants that are what we call climate change migrants. They're not moving for political reasons or warfare. They're moving because the climate has changed dramatically. They can no longer survive, and they must move to areas where they can grow food and to eat. Otherwise, they're going to starve. Okay, so we'll stop here and then we'll look at the causes of present climate change in the next